Welcome back to ECE 320A. We are closing in on finishing unit number 11. Don't forget you have homework number 11 due at the end of this unit. That's in chapter 15, which is our active filter unit, and our final exam is coming up at the end of our next unit, which is unit number 12. What we want to accomplish in this video is actually design a couple of filters that are third order low-pass Butterworth. And those two different designs will obviously have different specifications associated with them. In the first one, our A design, let's just do something fairly straightforward. Let's design a low-pass third-order Butterworth with a bandwidth of 1 radian per second. So you can see that I've already accomplished step 1 in our 6-step procedure. I've already been given the filter order, but if somebody gave you indirectly that filter order by telling you a particular set of attenuation and stop band frequency behavior, then you could find that n equaling 3 is what you have to obtain for this particular problem, or in this particular example. So let's now design a low-pass third-order Butterworth with a bandwidth of 1 radian per second, and that's really the bandwidth by default. All of our filters, polynomials, or those particular factors in table 15.1 are designed to produce a bandwidth of 1 radian per second. We then have to simply go to table 15.1 and find n equal 3. If we do that, we're now in this particular row, and we now see that we need one second order section, and we can determine what the B1 is for that particular section, and we need one first order section, and that one is always the same. If we have an odd filter order, then we're always going to have this S+1 factor, and that will always be achieved in the normalized case with the exact same filter. This is the denominator then from table 15.1. It has the first order factor S+1, and we implement that using the op-amp circuit in figure 15.1, and we have this second order factor S squared plus S plus 1, and that's now a second order section which we've looked at before in terms of a realization, this op-amp circuit, and that's in figure 1521. And just for fun, I went ahead and calculated or showed you the roots. You could write that many different ways. We could write it in this factored form that shows us the real part and the imaginary part of those roots, or the table is going to just give it to you in this very compact form of S squared plus B1S plus 1, and now B1 is sitting there, but it's kind of hard to see maybe because B sub 1 is actually 1 in this case. But the roots of that second order section are at -1/2 plus and minus j square root of 3 over 2. There's two of our roots. We have 3 because our order n is 3, and our third root, our odd root, is on the negative real line at s equal to -1. Our second order section then needs to have B sub 1 equal to 1. That's this particular value, or that coefficient. There's our B1, and that's 1. And B1 is used to determine C1. From our equating of coefficients, we now know that C1 is 2 over B1. B1 is 1, so that's not very hard to divide into 2. C1 is now 2. And C sub 2 is the reciprocal of C1, or 1/2. Now we have our second order section designed. And we already know what our first order section is, so here is our circuit. We've combined this, and it doesn't matter which one's on the left or which one's on the right. We just need to cascade those. So the output of one of these sections needs to be the input of the other, and the total overall input and output will obviously be the leftmost input and the rightmost output. But our first order section has R's and C's equal to 1, and that produces this 1 over s plus 1 transfer function with a denominator of s plus 1, which is what we want. And our second order section on the left, the way I've interconnected it, has c sub 2 equal to 1/2 and c sub 1 equal to 2, and that will then accomplish this denominator of s squared plus s plus 1, where the linear coefficient b sub 1 is equal to 1. And that's our design. That now provides us with a third order low-pass Butterworth filter that has a bandwidth of 1 radian per second. So it's maximally flat in the passband out to our cutoff frequency, which we've just had it set equal to 1 radian per second, and then it rolls off. And how fast does it roll off into the stop band? This particular filter. We have a third order filter, and each of those orders produces a minus 20 dB per decade roll off. So we're now rolling off in the stop band quite quickly. We're going down at minus 60 dB per decade if you now had to sketch the Bode plot. There's our design. It's a third order low pass Butterworth filter, and this is the realization. That's the circuit that you would have to build with those appropriate parameters to achieve a 1 radian per second bandwidth. And you can see that's a pretty small bandwidth, and those are pretty big capacitors, 2 1/2 farads. So now to become a little bit more realistic, suppose that we want a bandwidth of 200 hertz, not 1 radian per second. Then we need to compute our frequency scaling parameter, k sub f, where omega nu is equal to k sub f omega old, or k sub f is the ratio of omega nu to omega old, or omega sub 2 to omega sub 1. Omega sub 2 is, let's assume that omega sub 1 is what we just designed, and that's 1, so, and that was 1 radian per second. We need to have our new bandwidth frequency, omega sub 2, expressed in radians per second to be consistent, so that we have a dimensionless frequency scaling variable or parameter k sub f. Omega sub 2 is now then going to be 2 pi times 200, and omega sub 1 was just 1. So now we have a frequency scaling parameter, k sub f, equal to 400 pi. Suppose that somebody now actually wants the resistors to be 10K. Maybe they don't want these big resistors of 1 ohm, or they want a bigger parameter value of R of 10K, and the resistors are not frequency dependent, but they can be scaled in magnitude. So now R sub 2 is equal to K sub M R sub 1. And here's where you have to kind of remember what R's you're dealing with, but most of our R's are just R, so we can kind of get away with R sub 1 and R sub 2, but maybe not. So let's talk about R sub nu over R sub old. R sub nu, we want those to be 10K, and our R sub old, all of those have been 1 ohm. So now we have a magnitude scaling factor of 10,000. That means in our circuit here, where we have R's and R1 and R2 in this case are both 1, so they get scaled the same. Our R's in the second order section are always equal, and they started out as 1. So now we can actually use this magnitude scaling to say that the R bars, the new resistors in our second order section, will both be 10,000 times 1, or 10K. R1 bar in the first order section is 10,000 times 1, so it's 10K, and R sub 2 bar, in this case, it was the same as R sub 1 because we wanted that 1 radian per second bandwidth. This is now 10K as well. The capacitors provide us with a little bit more detail. So C1, if we go back to this expression, C unsubscripted is in our first order section. C1 and C sub 2 are associated with our only second order section. C sub 1 started off as 2. K sub F was 400 pi. K sub M was 10,000. And if you do that math, you'll now find a more realistic or reasonable capacitor of 159.2 nanofarads. C sub 2 was actually 1/2, which is 4 times smaller, or a factor of 4 less than 2. So we should see if C1 was 160, C sub 2 is going to be 40. So this one actually ends up being 39.8 nanofarads. And C bar was just C equal to 1, is 1 divided by the frequency scaling of 400 pi and divided by 10,000. This ends up being 7.96 times 10 to the 8th farads, or 79.6 nanofarads, or about 80, which makes sense since that is halfway between, or in a sense, a factor of 2 different away from 1/2 and a factor of 2 different away from 2. So those are now our capacitor values that we would introduce into this particular same circuit structure, but now different parameter values. All our R's are now 10K. C1 is 160 nanofarads. C sub 2 is 40 nanofarads. And C, up in the upper right, is the 80 nanofarads. And that's what we would need to do in order to accomplish a bandwidth of 200 hertz with a magnitude scaling of 10,000 for our particular impedance values. That's what we would do for a third order filter, and you should be able to now combine second order sections in the necessary amount in order to achieve the appropriate filter order that you might need given a particular problem statement.